Liam, how's it going?
Everything's fine. How about you?
Good. I'm excited for this second interview that we're doing here. Are you excited?
Yes, I am.
All right. So we are going to put 45 minutes on the clock, and I'm going to start the timer now, and then I'll give you the prompt. Sounds good?
Yep, I'm ready to start.
Okay, starting the timer now. So for this interview, we are going to work our way through at least a couple, maybe a few different problems that are all sort of related, and we'll start out with something perhaps simple that you might already be familiar with. But imagine you have a binary tree. So I'm going to paste here an example binary tree that's rooted at a node with value 1. We define the depth of a node in a binary tree as the distance from that node to the root node, or in other words, how many edges you have to traverse upwards to get to the root node from that node. So like the depth of the node with value 8 here would be 3. The depth of the node with value 1 would be 0 as the root node. Does that make sense?
Yeah.
So I want you to write a function that is going to take in this particular binary tree, or any binary tree, and it's just going to return the sum of all of the node depths in this binary tree.
Oh, okay. So in what form will the binary tree be given?
So imagine you've got a class. We've just got like a binary tree node class. If you want, you can just call it node. And it's got a value property, a left property, and a right property. And the left and right ones are going to point to the child nodes, or like the null value. And the value property is going to point to an integer.
Okay. So the sum of the depths. So call this sum of depths. And then I'll be given the root, right?
Yep.
Right. So what I'm going to do is I'll keep DF. First thing I need to do is find the depth of all of the nodes. So in order to do this, I'll just start a DFS from the top node, and then in the DFS function, I'll pass in the node and also the depth of the current node.
Okay.
And then each time I go down one level, I increase the depth by 1. So
okay.
So for each node, when I DFS onto the node, I'll know the depth of the node, and then in the DFS function, I also add the depth of the node to a global variable called answer.
Okay.
So guess I'll just write the code now.
Yep, sounds good.
So I have the answer, and then initially the answer is 0. And then we also want to return the answer in the end. And
okay.
We do our DFS, and we start from the root node. And the root node starts from a depth of 1. So we call DFS root 0. Then our DFS function, node u, and then we have the depth of the node. Okay, so once we have the depth of the node, we'll know the depth of node u is here, so we'll just add it to our answer.
Okay.
And then we also need to DFS to the left and the right children if there are any. So first thing I need to do is check if the left and the right children actually exist. So in C++, I think I can just do this. Oh, by the way,
okay.
This should be a reference, so I need to add stuff.
Sure.
And then if the left child is not null, then I'll do a DFS on the left child, and I'll add 1 to the depth, because the distance from the root increases by 1. And I'll do the same thing for the right child. And yeah, this looks good to go.
Okay, yeah, I think this would work on the binary tree. So this was sort of like the introductory problem here. Now let's assume we wanted to up things a little bit. We wanted to increase the amount of stuff that we're looking for. So here, you calculated the sum of all the node depths in the tree rooted at 1, right?
Yeah.
Now, let's try to write a function that is going to return the sum of all of the subtrees in this binary tree, in the input binary trees, all of the subtrees sum of depths. So like for this particular binary tree, your function, your sum depths here, would return, I think, 16. That would be the answer, right? Now, imagine we were also looking for the sum of the depths of the binary tree rooted at 2, the binary tree rooted at 3, rooted at 4, at 5, at 6. So all of the subtrees, and we want to add all of those node depths.
Oh, okay.
And the answer for this, so for the second problem, let's call it prompt number 2, but we're using the same input binary tree for the sake of the example. The answer would actually be 26. Are you understanding how I'm getting or computing this 26?
Yeah, I'll just calculate myself just to be sure. Okay, so the subtree rooted at 2 has a 6, and subtree rooted at 3 has 2. So that makes 24, and the subtree rooted at 4 has 2. So okay, so it totally adds up to 26. Yeah, I get what it is.
Yeah. Yeah.
How about I'll just move this part to the top?
Sure, yeah.
Okay, so I think since like the tree is like kind of a recursive structure, I think maybe if we calculate the sum of depths in the subtrees of 2 and 3, you might be able to use that information to calculate the sum of depths for the entire tree rooted at 1.
Okay.
Let's consider what happens to the depths when we move from when we move the root from 2 to 1. So when we move from 2 to 1, the depths of all 5 nodes in the subtree of 2 are increased by 1.
Okay.
Okay, so, and then similar thing happens for the subtree root at 3. So when we move the root from 3 to 1, all nodes in the subtree of root 3 are increased by 1.
Yep.
Okay, so in order to get the new sum of depths, we can take the old sum of depths of the left subtree, add that to the old sum of depths of the right subtree. And then in order to fix the fact that we moved the root to 1, we should add to that the total number of nodes in the left subtree and the total number of nodes in the right subtree.
Okay.
With DataCamp, you don't need to download Python to learn Python.
In my DFS function, so for my DFS function, I'll return 2 things. So I'll just make a pair for this. So DFS, and then node view, and then I don't know if I need the def right now, so I'll just leave it. I'll just leave the parameters like this right now. So for the pair that it returns, the first element of the pair will store number of nodes in subtree, and then the second element of the pair that is returned will return the sum of depths in the subtree at u.
Okay.
Okay, and then so let's initialize the result in the DFS function. So initially the pair, so the number of nodes in the subtree of u. If we don't consider the left subtree and the right subtree, then we only have 1 node, which is u itself. So the number of nodes starts at 1, and then the sum of depths will start at 0 if we only consider the node u. And after this, we'll consider the left and right subtrees if they exist. Does it make sense so far?
Yep.
Okay, so now we'll add the sum of depths of all of the nodes in the left subtree of u. So let's call this p child, and this will be returned from the DFS function when we for the left child. Okay, and then we add the sum of depths of all nodes in the left subtree. So initially we add the original depths, but then the original depths get increased by 1. So the total increase is the number of nodes in the left subtree.
Yep.
First, we add the original, we add the original sum of depths and plus the increase, which is just the number of nodes. Then that will give us the new sum of depths when we considered the left subtree of u. And we also need to update the number of nodes in the subtree of u. So to that, we just add the number of nodes in the left subtree of u. Is this part
right?
This part, does it make sense so far?
Yep.
Okay, so now this is for the left subtree, and we basically do the similar thing for the right subtree. I think we just need to change this. Yeah, I think it's all right now. So this DFS function will return. Oh yeah. Oh, I also need to add it to the answer. So store a global variable called answer, and then after I calculate the sum of the depths for the subtree of u, I add that sum to the answer. So I add the second value of the pair. Okay.
Right.
This is for DFS. Now, for the entire program, I'll just have something similar to the one before. It's called sum depths and then node starting from the root.
Yep.
Applies answer to 0. I call the DFS function for the root and then I return the answer. And yeah, this looks pretty much it.
Can you just quickly walk me through the example here at the top, conceptually, like if you were to run that function?
Okay, so first of all, we call DFS on the root, and then the DFS on the root calls like all these all of the children, and so the first nodes that return any values are the bottom nodes. So
yeah,
the leaf nodes 8, 9, 6, and 7. They don't have any left children or right children, so they'll just return the pair 1, 0. So these
and 5.
Oh yeah, and 5.
Yep.
Okay, and then after that, let's look at 4 and 3. So 4 and 3, they initially start at 1, 0. Then when we look at the left subtree, let's look at the left subtree. So the second value of the pair is added with both values in the subtree. So 1 is added, and then the first value of pair is added with just the number of nodes in the subtree, which is 1. And that's when we process the left child. Okay, I'll just once we process the left subtree, 1, 0 becomes 2, 1. And then
Yep.
process the right subtree becomes 3, 2. So the value of the pair returned by 4 and 3 is 3, 2.
Yep.
Okay, so now let's look at node 2. Node 2 also starts out with 1, 0. And after looking at the left subtree, which is 4, first we add it to the second value of the pair. We add both numbers, so it becomes 5. And then you also add the number of nodes, so then it comes 4. Now we move on to the right subtree. Right subtree is 5, so for the second value, we just add 1, and for the first value, we also add 1. So the pair returned by subtree 2 is 5, 6.
Yep. And just to make sure, the last thing before I think we can move on here, can you re-walk me through how you got the 5 here?
Okay, so in order to update the second value of the pair after processing the left subtree, I add the sum of depths of the left subtree and the number of nodes in the left subtree. So left subtree is 4.
Right.
So the sum of depths is 2, and the number of nodes is 3. So I add 2 plus 3, which is 5, into the sum of depths.
Yep. Okay, cool. So listen, I don't think we need to walk through the rest of the tree. I think we have the idea here. Let's move on to something completely different. Okay. Oh yeah, sorry, can you hear me?
Can you repeat the last sentence?
Yeah, so I said I think we can stop going through this example. I think this makes sense. And let's move on to something completely different, okay?
Sure.
So I'm actually going to copy paste another example. I want you to imagine that we had, or actually, you know what, let's just work off of this binary tree. We can just work off of this one.
Sure.
So we have this binary tree here. We've so far been able to calculate the depths in the binary tree, the depths in all the subtrees, right? Now, what if we wanted to calculate the distance of every node, not to the root, but to another node? So for example, I would give you like the node with value 3, and I would probably give you the root node of the binary tree as well, just so that you have the entire structure. And I wanted you to return the distance, or the sum of the distances, of every node in this binary tree to the node with value 3, or to whatever second node I give you.
Oh, okay. So each node will have a different value, right?
Value as in like the integer value? Yeah, but you can imagine that I would give you the actual reference to the node.
Oh, okay.
But so as an example, like if we were to call this function with the root node as like the target node, there's a target node, the answer that you'd be looking for would be the node depths, just your first question, right? The distance of every node against the root node, and you sum up those distances. But now what if I gave you as the target node, like another node, not the root node?
So the function will look like sum this, like this?
Yes. Yep.
Okay.
And the root in our case is always, like with the example that we had above, is always going to be 1. Or the node
Can you
with
repeat
value
that
1.
again?
Yeah, the root node in our example is always going to be the node with value 1.
Okay. Okay, so I think I need to maybe I need to pre-calculate some information for each of the nodes. Like maybe one DFS won't be enough. So I'm just wondering, can I create like more? Am I allowed to like add new variables into the node class?
Totally. Well, let's allow that.
Okay. So first thing is
and you can almost assume that, like, to your question, if you wanted to, you could first transform this entire tree into a tree that fits you or that you prefer, right? And then you kind of do whatever you want to do.
Okay. So each node will have left, right, have a value, and then we will also have calculate the sum of depths in the subtree of each node. So I'll just call this sum of depths. And in order to calculate the sum of depths in each subtree, can use what I just did up here. And so that'll be our first DFS, is to calculate this value, sum of depths in each subtree for each node.
Okay.
So, and then for the second part, I'm actually just going to end up calculating the sum of distances to each node, not just the target node. So what I'll do is I'll start from the root node. I know the sum of distances to the root node, and that'll just be the sum of depths. And I just need to know. I'll change this not sum of depths, but just the number of nodes in each subtree.
Okay.
Okay, so let's say I know the sum of distances for each node to 1. And if I know that, then can I figure out the answer for node 2 or node 3 instead? And the answer is actually yes, because what we'll do is, let's say that the current value is x, and in order to modify the sum of distances, notice that when we move the target node from node 1 into node 2, all nodes inside the subtree of node 2 will have the distances decreased by 1.
Yep.
And then all nodes outside of the subtree of node 2 will have their distances increased by 1.
Yep.
Right, so in this case, some distances for target node 2 can write that as sum of distances from 1 minus number of nodes in subtree of 2, because all these nodes have their distance decreased by 1, and we just add the number of nodes outside subtree 2 since they have their distances increased by 1.
Okay.
Okay, so in the second DFS, what I'll do is every time I call from a parent to a child, I'll use these two pieces of information to update the sum of distances. And in this way, once I DFS onto a certain node, I will know that node's sum of distances to every other node.
Now, can you walk me through your logic for this? So I understood what you just said, and I understood how you found this, the sum of distances for 2, but can you walk me through the same logic for like another node in the tree? Like for instance, let's say we went with a node with number 5 as the target.
As you're aware, the hardest part of scraping
Me through this logic.
Okay, so first the DFS will like first go to 1, then it'll go to 2, then it'll go to 5. So So now, in order to go from 1 to 2, we already have this formula, and now we need to go from 2 to 5, and we can use a similar formula as well. So sum of distances for 5 is equal to sum of distances for 2 minus number of nodes in subtree 5 plus number of nodes outside subtree 5. And
I see. So you are basically, when you find a node like node 5, you go to you treat its parent as the new like root node kind of, and you apply that function on that parent node.
Mm-hmm.
Okay. And just to clarify, for here, sum of the distance is 5. Okay, let's say we had gone with 8. So imagine, I'm going to type out something here. Imagine we had done sum of this of 8. What would you do here?
I'll just look at its. So first of all, the DFS will visit all nodes, and then
Yep.
8 is the only one we care about, so I'll only go through nodes 1, 2, 4, and 8. So when DFS from node 1, we have this value already, and then we'll starting from 1, we DFS to 2, and then using this formula, we can calculate the sum of distances for 2, and then from 2 we DFS to 4, and then using a similar formula, we can find the sum of distances for 4, and then then we DFS onto node 8, and we find that node 8 is the target node that we want. So then we'll set the answer to the sum of distances for 8.
And the formula would be sum of this on 4 minus number of nodes in subtree. In subtree, there would be no subtree here.
It'll just be like node. It'll be subtree 8. It'll just be the node 8.
Right. Okay. And then plus number of nodes outside your subtree, which would be node 9.
It'll actually be the entire tree except for 8. So in fact, I'll write this formula. I'll rewrite this formula a bit. So if n is
Okay.
total number of nodes, then sum of distances for some node u equal to the sum of distances for its parent minus the size of subtree of node u plus the number of nodes outside of the subtree. And we know that total number of nodes is n. So in order to find the number of nodes outside the subtree, you can just do n minus s of u.
Gotcha. Okay. Right. So you are adding not only the right subtree of the parent, but also all the other number of nodes because they all have like one more distance to the sum of distances of 4.
Yeah, exactly.
Or of the parent, rather. Gotcha. Okay.
Just so.
Let's try to code this out.
Okay, so start with the answer. And then for the first, so in the first DFS, I'll calculate the sum of the number of nodes in each subtree, and also the sum of distances for the first node. So let's see. So just copy the function from above. So we get the pair from DFS1 root, and then DFS1 will be pretty similar to this.
Okay.
So yeah, okay, we don't need to modify anything here except also, oh yeah, I need to remove this answer because that's not what we're looking for, and I also need to set the size of the subtree. So I'll just represent the size of the subtree with SC, and I'll set that to, that's equal to the first element of the pair. So after that, do you follow along so far?
Yep.
So after that, first I can find n, which is the number of nodes, and n will just be the number of nodes in the root subtree. And then I'll just write this first, return answer, and then we do the DFS2, and we maintain the sum of distances for each node, and we also just set the answer to the sum of distances for the target node when we find it. So DFS2 starts at the root, and then sum of distances for the root is just p dot second. It's just the sum of the depths because it's a root, and then we want to find target, so I'll pass that in as well. Okay, so here I have DFS2, takes in the current node, takes in the sum of distances for node u, and then also gives me target. And then the first thing is if we find that node u is a target, then our answer is just the sum of distances for the current node. So I'll just check for that. Then I'll set the answer to the sum of distances. And then given the information given the sum of distances for node u, we now want to find the sum of distances for its left child and its right child, and we also want to DFS on all nodes in the left subtree and the right subtree. So just do this for the left subtree first.
Okay,
so in order to find new sum, I use the formula back there. So it's the sum of the distances of the parent minus the subtree, the size of the subtree of the left child, plus the number of nodes outside of the subtree, which is just n minus the size of the subtree. Then after I find the new sum of distances, I can call DFS2 on the left child. Is this part good so far?
Yep.
Okay, and then I just do the exact same thing for the right child as well. And yeah, this should be it.
Cool. Okay, so can you walk me through? Let's maybe copy the example. Let's copy it down here. I copied it at the bottom of the doc. Can you walk me through? But let's go through the actual code and walk me through. Let's say if you've been looking for the distances to 4.
Can you repeat that sentence again? There was some issue.
So can you walk me through all of your code, and let's assume that the target node had been like 4.
Right. Should I go through DFS1 as well, because we kind of went through that already?
Not DFS1, just the main function here, and then DFS2.
Okay, so DFS1. After I call DFS1, get n is equal to the first element of the pair, which is just 9. Then also find that the sum of distances for 1 is second element of the pair, which is, it was 16, right?
Yes, but so this is where, for DFS1, are you using the solution to the first problem or to the second problem?
I wrote the DFS one. It's similar to the one for the second problem, where I return a pair, and the first element of the pair is the number of nodes, and the second element of the pair is the sum of depths.
Okay, and but the sum of depths, aren't you here doing the sum of all of the depths?
It's the sum of depths in the subtree of U.
Okay, and the sum of, so it wouldn't be 16, it would be 26 with what you wrote here, no? Or am I not following correctly?
It's not the sum of the depths of all subtrees, it's just the subtree for node 1.
Okay, and here you're doing p dot second plus or equal p child dot second plus p child dot first. But why are you doing plus p child dot first then here?
In order to update I think it helps if we look back at the original code here. So in the original code, in order to find the sum of depths for all subtrees, I add the second value of the pair for all nodes U. But then here I'm only considering here for p, I'm only considering the pair returned by the root.
Oh, I see. Okay. You only return, you don't add them all up is what you're saying.
Yeah.
Okay.
And so I received this information from DFS1, and that's when I start going to DFS2. So I do it on node 1 first, and the first sum of distances is just 16, and then I pass in the target, which is node 4. And this will give me the new sum of depths, new sum of distances. It'll set it to, so it goes to the left child. It processes the left child, which is 2, and then set it to 16 minus the size of subtree 2, which is 5, and then plus n minus 5, plus 9 minus 5. This total ups to 15. So yeah, this totals up to 15. And then after I find the new sum of distances, DFS2 is called on node 2 with the sum of distances of 15, and the target is the same. And in this DFS, for the left child, the new sum of distances is calculated to be 15 minus the sum of distances inside subtree 4. The number of nodes inside subtree 4, which is 3. And I add n minus 3, which is 6. And this totals up to 18. Okay. And then DFS2 is called on node 4 with value of 4, 18, and 4. Then here I have the if statement and sees that the current node is the target node, so the answer is set to 18. And then all the nodes are called by the DFS2 function, but I'm just showing like 1, 2, and 4 because it's they're the only ones that we care about for this example.
And you would return at this point, but in theory it would go to, or it could go to all the nodes. Like if you had like node 7 as the target, then it would go to all of them is what you're saying.
Yeah. Well, my code doesn't actually return, so it'll still go to all of them, but then it doesn't matter if it visits all of them.
Oh, right. Yeah, there's no need to return preemptively. Okay. And can you walk me through the complexity analysis of the solution?
Oh, okay. So for DFS1, the structure is, so for DFS1, you just basically go through each of the nodes once. So the complexity is linear time. And then for DFS2, we also go through each of the nodes exactly once. So it's also linear time.
Yeah, and you're not doing any other like costly computations and times because you already have computed values, right?
Yeah, I store the sizes of the subtree in the nodes already inside DFS1.
Yeah, and so from a space complexity point of view, what is this going to look like?
I think does the size of the subtree count as extra space?
I believe so. If you're going to be storing extra values, you'd be storing like n extra values basically. Yeah,
so that would be O of n extra space.
Yeah, and then the recursive calls are kind of disregarded because of this, and that's fine. Okay, and I guess here I think that's it. We can end here, William, with like 3 minutes on the clock roughly.
Okay, sure.
That's the perfect.